So just passed back your Chapter 3 tests. When grading them, I noticed that we didn't talk about something that I should have, and I threw out, I think, 2 questions, I think 9 and 14 or something. So that's why there's like the big slash to that question or whatever, because I just didn't count it for anybody. So I want to talk about the tool that we should have used to kind of do those kinds of questions, because again, occur on the IB exam. So let's talk or take some time and kind of do some examples and talk about the tool we use to do that. Very good. The tool you're going to need to use, or that I recommend you use to do this, you don't need to, but like, come on now, that's the way we're going to do it, is using your calculator. So if you have your graphic calculator with you, I invite you to take that out to follow along. If you want to borrow one, there's a couple on my desk. You're welcome to grab one to borrow. If you want to follow along, this is why supplies last anyways. So, what we're going to need to do on our graphing calculator is we're going to turn the calculator on. We're going to find the apps button. That's not short for appetizers, but applications. Although I could go for some cheese sticks right now. So I press the apps button, and the tool that we're going to want to use here is finance. Now it should be installed on everybody's calculator automatically. You may not have all this other junk that I have on mine, but you should have the finance. And the particular finance tool that we're going to use to do any of these, like compound interest or payments or loans or annuity or whatever the type of question is going to be this TVM solver. So we're going to pick that option 1. Okay, and I've gone and pulled, a half dozen or so questions from the homework. And we're just going to kind of do these questions using that solver as our tool to complete them. So you get a feel for like how the solver works and how to use it and how to input parts of a story problem into the solver and get the, the desired information to kind of hop out of it. Okay? So the question here says, at the beginning of every month, Maggie invests 150 pounds in an account that pays 6% annual interest. How much money will there be in the account after 6 years? So the solver here that we have has this set of inputs here. The capital N stands for the number of compounds that we're talking about. The I with the percentage is the interest rate written as a percentage, not as a decimal. PV is the present value, that's the initial amount invested. PMT is the payment, so if you're making a regular investment or paying off a loan, that's talking about a payment. FV is the future value, so that's like what will happen in the future. P/Y is the number of payments per year. And C/Y is the number of compounds per year. So for this question, we're going to be putting $150 into a bank account that every month for 6 years. So the number of compounds there should be 6 times 12. Right? We're doing this every month for 6 years. And notice that I could just type in 6 times 12 and press enter, and it'll do the arithmetic for me. I don't have to do it on a separate. I can just type it directly into there. The interest rate in this question is quoted as 6%. The present value, how much started in this bank account before we started making our regular payment? zero, right? The bank account is empty until we put that $150 in, and we're gonna do that regularly, so that's the 150. Now, the solver has some like directionality built into it. So when we're taking that $150, it's leaving Maggie's pocket and it's going in the bank, right? So in a way, that's like negative money because it's coming out of Maggie's possession and going somewhere else. So we're gonna write that the payment as negative $150 because again, like there's a directionality, there's like a flow for the money. So if the money is leaving your possession, you're gonna think about that as like a negative number. And if the money's coming back into our possession, that'd be like a positive number. Everybody's okay with that idea? The future value is what we're looking for, so we're gonna skip that for now. How many payments are we making into this bank account per year? 12, because we're investing $100, $150 every month. And how many compounds are happening per year? Again, we assume that that's 12. Typically, anytime you're doing something, making a regular payment monthly, the interest is accumulating monthly. So to get the future value now for this, that's the piece that I'm looking for. I'm gonna move my cursor so that it's on the future value. See how my cursor's next to FV? And I'm gonna just press alpha and enter. So at the end of those 6 years, we should have $12,961.33. How nice is that? Pretty easy, right? Okay. Go on to the next example. Sound good? We're just gonna do, I don't know, I have 6 or so examples here. Maybe 7, 6 or 7. All right. So the next question says, each month Suzanne invests 100 euros in an account earning 4% annual interest compounded monthly. Find the value of her investment after 20 years, assuming she started with a 0 balance. Okay, well that's fairly straightforward, right? So what should my N be?
12 times 20.
12 times 20, perfect. We're doing this every month, so that's the 12. For 20 years, that's the 20. What should my I be? 4. The present value? 0. The PMT? Negative 100. And what are we looking for? The future value and the payments per year and compounds per year should both be 12, right? Okay, so what do we press to get the future value to spit out? Alpha and enter. So $36,677.46 or something. Yes, Tia.
Does it make a difference if you begin and end with 12?
Yes. Brooks.
What number did you put in to let it know that it's after 20 years you want the amount of money after that?
The capital N is the number of compounds, which is 12 times 20.
Oh, okay.
Right? We're doing this every month, so that's the 12 for 20 years. That's where the 20 came in.
There you go.
Yes,
Do
Colby.
you always leave it on the end one?
Yeah. All right. Part B says, how much initial balance would we have had to start with if we want to make no monthly payments and end with that same amount of money? So here, what are we looking for in this question? a present value, right? That would be our initial investment. And our payment now is supposed to be 0, right? We want to find out how much we'd have to invest straight away to end up with the same amount at the end as if we paid $100 a month for 20 years. So again, I'll just turn the payment to 0, alpha enter on present value. We would have needed to invest $16,502.19. Is everybody okay there? The solver makes these quite a bit easier, right? To just algebraic, basically to remove all the algebra from it. You just have to like read the question, put the numbers in the right spots, and bingo, bango, bongo, here's your answer. Everything going okay so far? Okay. Let's move on to another question. Each month, Maxine invests 150 pounds in a fund for her retirement. The fund earns 6% annual interest compounded monthly. Find the value of her retirement fund in 30 years. Try this on your own real quick and then I'll punch through the answer. Give you a chance to check your own understanding. Make sure you're being able to use this solver competently. So there's my inputs. And our answer. Is that what you guys got?
Yeah.
All right. Part B then says, what if we put 200 bucks in instead of 150?
Would you have to change the end to, because it was how much you were putting in times the amount of years, so it was 150 times 30, would it be 200 times 30 now, or?
No, it was 12 times 30.
But we increased the money to 151.
Cap N is the number of compounds. It has nothing to do with the amount of money. So it's 12 years, or 12 months for 30 years. So it's still 12 times 30. Doesn't matter how much you're saving.
Oh, never mind.
Right? The Cap N is about the time. Are you okay? All right, let's do the next one. Here it's asking, how much do I need to save per month to end up with $4,000 when I earn 4% interest compounded monthly over 5 years? So try this one on your own. I'll give you a minute or two and then I'll key it in and show you the inputs that I would have used for the answers. $60.33. I guess I should probably say 34 cents to make sure I get over 4,000. And I probably should say at least $60.34 because it asks for within 5 years. So as long as you're saving more than that, you'll get there. You know, if you saved $100, obviously you'll make it. Everybody okay with that? Again, this problem algebraically is a pain in the tuchus, but like the TVM just eats it up, you know, like it's no problem at all. It's a 10-second problem or whatever. A loan takes 10 years to repay at $450 a month. The annual interest rate for the loan is 5%, and the loan is compounded monthly. Find the initial value of the loan. The initial value of the loan is going to be how much you borrowed, right? So again, take a minute, see what you can do. I'll go key in the inputs and get the answer here in a second for you to check against. So the key here is realizing at the end of the loan, how much do you owe the bank? 0, right? So the future value on that loan should be 0. So it says that I took out a loan for $42,426.61. Is that okay with everybody? Worth noting here that if I wanted to compute how much I actually paid the bank, if I do 120 times 450, I think it's 54,000, which is more than the 42,000 that I borrowed. It's like a nice check you can do at the end, just to make sure your answer is plausible. Because looking at this, I'm not sure, you know, like, who the heck knows, 42,000, I guess, that seems okay. But you can compute how much you actually paid the bank really easily, right? 10 times 12 times 450, and make sure that that amount is, you know, reasonably more than what you borrowed. I mean, you wouldn't want it to be like, oh, I paid the bank $2 million and I borrowed 42,000. I'd be suspicious there that I don't have the correct answer, even though the one is more than the other. All right, let's do part B then. Calculate how long it takes to repay the loan if instead we paid $900 a month. So we'd answer, what would I write as my answer then?
Um, 53.
53 months. Months, really, because that's, the compounds are happening per month. Yeah, so like 53 months. Now, why did you round that up?
Because if you did 52, it wouldn't be done because you gotta take into account the decimal.
Yeah, so even if that was 52.1, our answer would still be 53, because our last month payment would be not $900, but it would still have a payment that 53rd month. Everybody's okay? We feel good about using the solver. And I'm gonna skip this last question just because I don't feel like doing it. Everybody better on the solver? You feel confident you could use this again? Makes life quite a bit easier, right? Today, we're gonna start talking about chapter 9. For chapter 9, we're not gonna do a test because chapter 9 and 10 are like, you literally can't do any of chapter 10 without chapter 9, and there's not that much in chapter 9. So we're gonna do a chapter 9 quiz. That quiz will be like probably a take-home variety. We'll do a chapter 10 quiz and a chapter 10 test. And obviously, like, the skills from chapter 9 are gonna be all over the chapter 10 quiz and test. Like, you can't do one without the other. Yeah, Evan?
I think my calculator is broken.
Okay.
Like, it just keeps, I've been charging it for like 10 minutes and it just keeps doing this screen.
I think you have a corrupted battery is usually what that means.
Alright.
This is?
I've been charging it for like 10 minutes.
Yeah, mine did it. It's gonna be battery. You can charge mine if you want. Please.
You need to charge it?
Yeah, and I don't want to walk over there, so. Thank you.
So chapters 9, 10, and 11, we're gonna do all here right in a row. These are our calculus chapters. So outside of Brooks, this is gonna be new for everyone. So there's not like, oh, we've kind of done this before, I kind of hand wave my way through it. We're gonna go carefully and try to do this reasonably well. Now, the level of rigor that the IB requires for this is not terribly high. So I will hand wave some details Brooks will notice, probably none of the rest of us will, but that's okay. I'll give you like what the idea is, and I'll do an example, and then we'll like go straight to the shortcut and kind of skip a lot of the derivation detail, which I think is appropriate for this kind of a course, just to give you an idea of what's happening here, okay? So what we want to do is we want to start at talking about something called like an average rate of change. And when you hear average rate of change, you should think slope, right? So for example, if you traveled 100 miles, in 2 hours, your average rate of change would have been 50 miles per hour, right? You just took the change in time, or change in distance divided by the change in time. Now, on that trip, were you going 50 miles per hour the whole time? Probably not, right? You got in your car, you backed out the driveway, you came to a stop, you put it in gear, you go to a stop sign, you slow down, make a turn, you get on a road at a different speed limit, you're going faster, slower, and you come to another stoplight, and like, your speed's gonna be going up and down the whole time. You're probably only going 50 miles an hour for some small portion of the time. The rest of the time you might be going faster, slower, whatever. Is okay? So let's look at calculating the average rate of change. on some function. So remember, like when we say average rate of change, we just are talking about slope. Okay, average rate of change is just slope. So what I'm going to do is I'm going to do y with 3 plugged in minus y with 0 plugged in over 3 minus 0, right? Where like my x1, y1 is just 0 comma y of 0, and my x2, y2 is going to be like 3 comma y of 3. Everybody okay with this idea? We're just talking about points, calculating a slope. The notation looks a little funny, but that's okay. We can deal with notation if I just hammer away at you that it's just doing slope. So y of 3, 9 plus 6, that's 15, plus 3 more, that's 18. Y of 0, 0 plus 0 plus 3. So that's 15 over 3, which is just 5. Everybody okay there? Visually, what this is would have looked like then so here's like 0, 3, and here's like 3 comma 18, and the line that would connect them should have slope 5. All right, that's essentially what we did. Everybody okay conceptually, kind of what we just did there? Very important that we understand this concept, that we're comfortable here, because we're going to iterate on this idea. But all we're really doing is calculating a slope, right? Now, is the line from, or is the curve from 0, 3 to 3, 18 actually a straight line? No, it's part of a parabola. Like that's a curved line, right? What I've drawn is like, you know, a line between 2 points on that curve, but it's not actually the, you know, those 2 points don't form a straight line on that curve. Everybody's okay? So if anybody asks for average rate of change, you're going to be calculating slope. So y2 minus y1 over x2 minus x1, or change in some quantity divided by change in the other quantity, right? Now, that's an Algebra 1 idea, right? Average rate of change, this is something you've seen a bunch of times. The new idea, the calculus idea, is this idea of an instantaneous rate of change. So if you're driving your car and you want to know how fast your car is moving at that instant, what do? You look at the speedometer, right? So the car has this displayed for you. How is the car calculating this? It's looking at how fast the axle is spinning, and it knows how big the wheel is, so it's going to calculate your rate of speed based on that. Okay? But it's still giving you an average rate of speed because it doesn't know how fast that axle is spinning in the instant. What it's doing is it's taking a very narrow slice of it, right? It's taking over a quarter of a second, you know, how fast this is doing, and it's using it as an approximation. Or some sliver of time. I don't know how the actual mechanics of how they're making that measure, how the car is making that measurement, but it's still actually giving you a average rate of change It's just doing it with such a narrow sliver of time that it is good enough to call it instantaneous, right? And that's actually the idea here. So and I'm going to say, let's make this -2, because that's this point here. So if I want the instantaneous rate of change at a single point, if I try to use the slope formula with 1 point, what is the slope going to come out as? So if I do y2 minus y1 over x2 minus x1, and x1 is equal to x2, and y1 is equal to y2, what do I get?
0.
Nope. Nope, not quite. I get 0 over 0, right? Now 0 over 0 we've called undefined in the past, but it's actually worse than that. 0 over 0 is something called indeterminate, which means that I can write an expression that'll evaluate to 0 over 0 that I could also make equal, say, 1, or 2, or 3, or 10, or infinity, or negative infinity. It could be anything, it could be literally anything. Well, that's bad for us, right? So here's the idea. We're going to do much like your car does. Do not here. So we're going to pick some point, and we'll call that point just h units away from -2, 0. If I have a second point that's h away, I can calculate the slope of a line, right? And what I'm going to do is I'm just going to let h then approach 0. So what's happening? I'm doing essentially what your car speedometer is doing. I'm just going to keep getting that h closer and closer and closer and closer until I can make it a good approximation of what that instantaneous velocity is going to be. Because the closer those points get together, the better the approximation of actual instantaneous rate of change should be. So for example, for some h's, maybe I have 1, 0.1, 0.01, 0.001, and we'll calculate some slopes for those. And we'll use that pattern of what's happening to make a guess as to what the instantaneous rate of change is going to be. So I'm going to use my calculator to do this. Because it's a lot of repeated arithmetic and it's kind of a hassle. So I've started by pressing the y equals button and inputting the function that we're looking for the instantaneous rate of change in to my calculator, into the y1 spot. Then I'm going to exit out. And I'm going to do make a fraction, and I'm going to do y bars, bars, y bars function y1 of -2 plus 1. That's my y of x plus h, right? Because my h in this first case was 1. And then I'll have minus we'll do bars, y bars, function y1 of -2 over -2 plus 1, that's my x, minus -2, that's my other x. So there, the slope is 0. And then I'm just going to go ahead and update this. So where it said 1, I'm going to change that now to 0.1. And I'm going to just keep picking h's that are getting closer and closer to 0 and see what's happening with the slope. So now it's -0.9. We'll change it to 0.01. -0.99. And we'll change it to 0.001. I think that was the last thing in my table. It's pretty clear at this point what the slope is going to. What does it look like that the slope is approaching?
-1.
-1, right? Is everybody okay with that? The closer that h is getting to 0, the closer the slope is getting to -1. What is that called that we're doing here? When we look at what's happening as like one variable approaches something, what is the other variable approaching? It's called a limit. You remember that from pre-calculus last year? So in general, our instantaneous rate of change can be found by looking at the limit as h approaches 0 of f of x plus h minus f of x over x plus h minus x. Everybody's okay? So let's do this. Use this formula to find the instantaneous rate of change for the function x squared minus 1 equal to 0. So my f of x in this case is x squared minus 1. So f of x plus h would be x plus h squared minus 1. And then minus f of x, so minus, and I have to make sure I put a parenthesis around that because I'm subtracting the whole thing, over x plus h minus x. So far, so good. Those guys cancel out, right? And I'm going to FOIL out. Oops. I did a bad thing here, guys. What did I forget? Got my limit. Ah! Okay. FOIL that out. I get x squared plus 2h plus h squared minus 1 minus x squared plus 1 all over h. Everybody okay with the algebra so far? Just FOILed some stuff out, distributed a negative, find some like terms. So the x squareds combined to give me 0. The -1 and +1 combined to give me 0. So I'm left with 2h plus h squared over h. Everyone so far so good? No mistakes yet? I don't think. So I can reduce this, right? Because you can think about like factoring an h out front, so that can reduce. And as h is going to 0, what does 2 plus h go to then? 2, right? What happened though? Because that's not the right answer. Where's my mistake?
I was gonna say, for the equation part, like you plugged in x squared plus h, but it wasn't the same for the other part.
Well, this is f of x plus h, right? And this is f of x. Oh, Mr.
Yeah.
Kulik, you're so dumb. I got it. I got it. X is equal to 0. So the x's are supposed to be zeros. There we go. So that's just going to be h squared minus 1 plus 1 over h. There we go. Those guys cancel out. It's like, that's not what it's supposed to happen.
Raise the restroom.
Yes.
Shut up.
Now, this process that we just did stinks. Like, this stinks. This was a pain in the butt. The algebra is kind of crummy. If that function was more complicated than x squared minus 1, this gets worse. The more complicated these functions get, yuck. There's a better way. So we're going to define a new function . So that new function that we're going to define is called the derivative. So we say that the derivative of f at the value x equals a is the same as the instantaneous rate of change of f at a. That's the thing we've just been doing, which is the same as the slope of the line tangent to f at a. When I say tangent, what we mean here, if I go back for a second, so if I take this picture here, we want to draw the tangent line, it would be like this. That's the instantaneous rate of change, the slope of the line that passes through that point that's like tangent to the curve. And as h goes to 0, that blue line eventually turns into the green line, right? You can visualize that as h is getting closer and closer and closer to the red point, that those two slopes will converge down. So if we give this, we've given this operation a name, this derivative operation a name, we need a symbol to go along with this, right? Just like if we talk about how to find a square root, I need a symbol to indicate like, hey, take the square root of this. We need a symbol that means take the derivative of this. That symbol is going to be this d over dx symbol. So this is the derivative operation. So if I say dy dx, that means that we did the derivative of y. Or the other notation that we might use is, if I have like a function notation, if I put a prime on it, that's also going to mean the derivative of f. Okay, so just introducing some notation because we're about to give you some shortcuts on how to calculate these derivatives so we don't have to do this whole limit of a difference quotient thing. Is everybody okay with the notation so far? We'll do a bunch of examples here in a minute to help hammer that home. So there are only 4 derivative shortcuts that we're going to need for this course. In reality, Brooks, how many derivative shortcut formulas do we have?
Only one.
Like a couple dozen, right? The shortcuts for all the different function types.
Is it not just one where like you decrease the degree
But-
of one?
Yes, that's the one. That's one of them. Yes.
Yeah. Okay.
But there's like one for tangent and cosine and sine and inverse tangent, natural log, and e to the like
Yeah.
there's a whole boatload of these things, right?
Mhm.
So there's only 4 that we need to worry about in this class. I think I have to double check that, but I'm pretty sure it's just these 4. The first is that the derivative operation can distribute across addition and subtraction. If I have the derivative of, the sum or difference of some stuff, I can look at each piece in the sum or difference separately as its own separate derivative problem. Is okay there? Okay. The second is that I can, by taking the derivative of a constant times some function, I can ignore the constant, take the derivative of the function, and then multiply the constant in at the end. Is everybody okay with that idea? We'll do examples here in a minute, and it'll be clear how we'll use these things. The third rule is that the derivative of any constant is 0. And our fourth one if I have take the derivative of any power function of the form x to the n, the result is going to be n times x to the n minus 1 for all n except for negative 1. For reasons that are outside the scope of this class, the derivative of x to the negative 1 is the natural log of x. I should say the natural log of the absolute value of x. All right. So our first example, we're asked to calculate dy dx for y equals 3x squared plus 5x minus 1. So what that means is dy dx is the derivative of this polynomial. First thing I notice is that I have sum and differences in this polynomial. So I can distribute that derivative operation across the terms of the polynomial. That's me just using that shortcut number 1, right? Notice in the first derivative I have 3 times x squared. That 3 is like a constant. I can use shortcut 2 to pull that constant out front. I can do the same thing for 5x. Is everybody okay there? So if I look at my derivatives I have left, I have something in the form x to the n, something in the form x to the n, and then a constant. I have a derivative rule for each one of those situations, right? So using rule 4, the derivative of x squared is going to be 2x to the 2 minus 1. So the exponent becomes the coefficient, and I subtract 1 from the exponent. Mr. Kulik, if I look at x, I don't see an exponent there. What is the exponent? 1. Oh, there is an exponent there, right? We just don't write it. So I have 1 times x to the 1 minus 1. Everybody okay? And then the derivative of 1. Well, 1 is just a constant. What's the derivative of a constant?
0.
0. Everybody so far so good? Now we'll just do a little bit of simplification and we're done. 3 times 2 is 6. 2 minus 1 is 1, so I'm not going to bother writing a exponent of 1. Plus 5 times 1 is 5. X to the 1 minus 1, well, that's x to the 0. What's x to the 0? 1. And then minus 0 is, doesn't do nothing, so there's my final answer, 6x plus 5. Everybody's okay with that?
Yes.
Okay. if I had added this as all that means is at the end is I'm going to plug 1 in for x. So my final answer is just a number. Okay? Two different types of problems. One is I take the derivative of a function, I get a function back. The other is if I want the derivative at a point, I get a number back. Right? Now the process is identical, except for the final step where we plug the number in. Right? But it's same process. I'd like to do another example, or a couple more examples on this. Is that okay with everybody? Still hanging in? Okay. Oh, no, Mr. Kulik. What do you see that's problematic here? Square root. There's something even before that, though, that's a bigger problem.
Oh, it's.
It's a quotient.
Oh, God.
Right? Do I know how to do the derivative of a quotient?
No.
No. And you're not going to learn how to do it in this class. There is a specific formula to how to do this, but this problem can be done without that formula by just doing some simplification. So notice that the denominator in this fraction is a monomial. So we can rewrite this this way, right? Everybody's good with that? Since the fraction was a single monomial, I can just write both terms of the numerator over the denominator. Now, x to the fourth over x. I hope nobody has a problem reducing that to x to the third. What am I going to do with 3 square root x over x?
It's just x to the power of 1,000, so you just write it like.
Yeah, so we know the square root of x is the same thing as x to the 1/2. So when I divide x to the 1/2 by x to the first, I get x to the negative 1/2, right? Because what are we doing with the exponents when we divide? Subtract. So I have 1/2 minus 1. And now this is in a form where now I can start doing my derivative. So in some of these cases, there's going to be some algebra preloaded that you have to grind through to get it into a form where we can apply our derivative shortcuts. Namely, I have to get it so that like any multiplication or division is done. So I have just like single terms. Those terms, the variables in those terms, all have to be written as like a power function, x to some power. Okay? All right. First step, I can
Move the derivative.
distribute the derivative operation across the function because there is a subtraction going on there. The next step I would look to take out the constant. And now I'm ready to apply my power property, or the power rule here, and take my derivatives. What is the derivative of x to the negative 1/2 going to be?
X to the negative 2/3.
Negative 1/2
3/2.
times x to the negative 1/2 minus 1, which is negative 3/2. I'm gonna write out more work than we would be at this point. Yeah, Brooks has done this a million times. And the derivative of x cubed is 3x to the 3 minus 1. Is everybody okay with the work I'm showing? I'm trying to be really detailed and showing like a lot of steps. In another class or two, we're just going to do these things in our head because it should be, once you're comfortable here and you've done a little practice, this is stuff that you realistically should be able to just crank through without a big deal. Everybody okay? How I ended up here? Sure. Okay, keep cranking and do some more exampling here. Is everybody okay?
So if you final answer?
Oh yeah, that's where we stop. That's our derivative. It's a function. Because I just asked for f prime of x, not f prime of 7 or something. Mainly because I was scared of picking a number that I had to take the square root of at the end, and this problem getting away from me a little bit. Okay, this time we're asked to calculate f prime of negative 1. I'm going to do that. Since I picked a negative value, make sure I have a real answer coming out of this. Okay. So when I look at this, the first thing I notice that's a problem is we know how to deal with the roots. There's a bigger problem in our midst.
Oh, fraction.
Nope, not the fraction.
Multiplication.
Nope. It's that I have the product of two functions. I have the square root of x to the fifth, or I'm sorry, the fifth root of x times the seventh root of x. Do I know how to do the product, take the derivative of the product of two functions? No. Is there a rule to do that? Yes. Are you going to need to learn it for this class? No. Which means that we can accomplish the same thing via algebra and just getting rid of the multiplication here. So I'm going to start by rewriting all these x's as power functions. So the fifth root of x is the same as x to the 1/5. The cube root of x is the same thing as x to the 1/3. 1 over x is the same thing as x to the negative 1. Oh, rats. I'll make that 2. Sorry. I don't want to take the derivative of x to the negative 1 because that uses a derivative rule that you guys should know. Sorry about that. So I'm going to make that 2. Okay. How do I multiply two things with the same base but different exponents? Add the exponents. To add 1/5 and 1/3, what do I need? Common denominator. What would the common denominator be? So I get 8/15. Everybody trust me on that? Okay. Now I'm in a form where I'm ready to take the derivative. Is everybody okay with the algebra that happened? Notice that I had to get this down to like power function plus or minus some other power function, right? Can't proceed if I have the product of functions, if I have the quotient of functions, if my functions aren't written as power functions, have to be power functions only. Okay? No products, no quotients. Everybody ready? Okay. So if I'm going to find the derivative now, take the derivative of this function. First thing I do is distribute across. You guys starting to feel like you're getting the hang of this? Next step is I look for constants. Do we see any?
Yes.
Yes, what do we see? The 7. And now I can apply my power rule. So the derivative of x to the 18/15 is going to be what's the coefficient? The same as the exponent, 8/15. And the new exponent is going to be
8/15 minus 1.
8/15 minus 1, which if you wanted to shortcut straight there in your head, that is okay. You don't need to write that step. I'm going to write it now because this is the first time you guys are doing it. This is day 1 of doing this. I will write out the work. That's going to be abandoned fairly quickly because it's kind of obnoxious to keep writing it and make all this extra steps when these are problems that eventually we should be able to do in our head. But I acknowledge that this is day 1 and you're not doing these in your head anymore. But that's the goal, is to get there. Okay, the derivative of x to the -2 should be
-2x exponent -2 minus 1.
excellent. And now we just simplify here, right? So 8/15 minus 1 is -7/15. -7 times -2 is 14. -2 minus 1 is -3. But remember, this question asked for f prime of -1, right? So now I go back and I plug in -1 for x and I simplify. What's the 15th root of -1? -1, right? Because it's an odd root. I should get a negative answer. What's -1 to the 7th power? -1 still, because it's an odd power. And what's the reciprocal of -1? -1. So we did that, right? The 15th root was the denominator of 15. The 7th power was the denominator of 7. The reciprocal was the negative sign. It's all still negative. It's all still -1. What's -1 to the 3rd power?
-1.
-1. What's the reciprocal of -1? -1. And now we just would make a common denominator that I don't feel like doing because it's gotten away from me, because 14 times 15 isn't something I want to do right now to make a common denominator and the 2 fractions, but like good enough for us, right? Is everybody okay? If I had asked for just f prime of x, this guy would be our stopping point. Because we asked for f prime of -1, we had to go a little bit further and plug -1 in. Is everybody okay with the difference in the notation and what we're saying? this feels like a good place to stop here for today. We'll continue talking about derivatives and what we can do with the derivative and like some relationships to physics, because boy, the IB loves physics. Next time. But this feels like a good stopping